Chemistry time. Today, tea drinker, polyatomic ion memorizer, David Keim, will tell you about covalent bonds. Covalent bonds. You already know what's going to come here pretty soon. But first, let's write down the objective. Investigate structure and function of covalent bonds and covalently bonded compounds. I bet you can see there's a relationship between those two things. As I'm erasing this, I can feel myself forgetting what I just said. So will you please remind me? Will you repeat the objective? Investigate. Structure and function. Hey, where did I get the terminology structure and function from, do you reckon? Does that remind you of anything?
Ionic bonds?
No. Of covalent bonds and covalent, ooh, this is not going to fit. It's because I chose to have just investigate be on the covalently bonded compounds. Ugly. Hey, where'd the language structure and function come from? I mean, those are words. They're English. That's not what I'm asking. Where did I get that terminology from? Do you know?
The structure and functions we find in everyday.
Yes, and we call that group of topics that pertain to all, we might say of the subject of science, but they pertain to all of nature. We call those concepts cross-cutting concepts. Yes, structure and function is one of the cross-cutting concepts. So one of the things we talk about in all different sciences is how things structure affects and is affected by their function. And we're going to talk about that in covalent bonds today. Now, the thing you knew was going to come, what am I going to ask you about? I've written the topic here. What am I going to ask you first, do you reckon? This is the discussion part. What am I going to, I do this every time. What am I going to, actually you don't know because you've only had 2 of these this year, and then before that it wasn't since last year. But what am I going to ask you?
You're going to ask us where do covalent bonds come from?
Okay, yeah, where does the word covalent bond come from? What does this mean? Well, let's talk about bonds first. What's a bond? We talked about this last time. I remember making the analogy of holy matrimony, that is of marriage, that a bond in marriage, it holds 2 people together, ideally, right? We know that's not always the case, but the idea of marriage is that it holds 2 people together, as it were, through thick and thin. And a bond is similar. We talked about ionic bonds, that a bond holds 2, in that case, ions. In this case, it'll be atoms in general, together. So what's the prefix co mean? You know? If you were to cooperate with someone, you would be operating together with them. If you were to cohabitate, which you shouldn't, you're too young. If you were to cohabitate with someone, you would be habitating, you would be living together with them, right? So together. And then what do you think valent refers to? What about you, Faye? You just came in, but tell me, what do you think valent refers to in covalent bonds?
Covalent bonds? Shares electrons.
Yeah, together, and then valent refers to?
Valence electrons.
Yeah, valence electrons. Good. So we talked about valence electrons last time. You can review that by watching the last video, or reading the last chapter, or finding a good YouTube video. But these are, so we know that this is going to be bonding. That is something that holds together by the valence electrons. And so that, when we break it down like that, it makes us realize that we probably could have technically applied that same terminology to ionic bonds, that it had to do with their valence electrons. It had to do with bonding, that is holding them together, and they are together. But in this case, it's telling us that the valence electrons, and this is the primary verb we're going to be using for this, is that they share. So just like in cooperating, you are sharing an operation. In cohabitation, you are sharing a habitation. The co, in addition to being together, kind of means share. And so the covalent bonds are those where valence electrons are shared. And that's it in a nutshell. I mean, if the video was only going to be 4 minutes long, that would do it. It's a bond that is sharing of valence electrons. But let's talk about that in a little bit more detail. Easy rule of thumb for covalent bonds is that generally they form between, well, why don't you tell me? Form between
groups 3 and 7.
Okay, yeah. Specific, not all of groups 3 and 7, But they form between what? What kind of atoms? Would indium or thallium form covalent bonds, do you think? It's in group 3. No, probably not. What about, yeah, there you go. Between nonmetals, good. And you'll realize this is filling the gap that we had from last time where we talked about ionic bonds formed between a metal cation and a non-metal anion, or a polyatomic ion in either case, and metallic bonds formed between metals, and now we're talking about covalent bonds, which primarily, and as a rule of thumb, form between non-metals. So give me an example of a non-metal.
Oxygen.
Okay, good. I'm glad you chose that one. There are a couple that would be great choices, and that was one of them. If I have, for instance, 2 oxygen, well, actually, let's just start by talking about 1. I have 1 oxygen atom. Tell me, what would its Lewis dot diagram or electron dot diagram, those mean the same thing, look like for oxygen? 6. Yep, 6 electrons? Valence electrons, right. It actually has 6 valence electrons. It has 8 electrons altogether, but we only indicate the valence electrons on the Lewis dot diagram or the electron dot diagram. Is it happy with its 6 valence electrons? Happy. Is it stable with its 6 valence electrons? It's electrically neutral because it has the same number of electrons as protons, but it's not.
Reactively unstable.
It's a reactively unstable, very good way to put it, because it is more stable with a full valence shell, with a full valence orbital, which would be how many for oxygen? 8. So it would be more stable chemically with 8. And we talked last time about how it could receive those electrons from a metal, for instance, calcium, forming calcium oxide, but that would form an ionic bond, where calcium has given its electrons, oxygen has taken them, calcium now has a positive 2 charge, oxygen has a minus 2 charge, and they're held together by electromagnetism. But another thing it can do is if we have another oxygen, I'll just put it back where I erased it from, if we have another oxygen with the same number of valence electrons, because it's the same thing, it can do this. It can share its valence electrons, and so now this oxygen has how many? Let's count them up. 8. This oxygen has how many? 8. So they're both more stable like this, and it has formed the molecule O2. Molecule is a word we use to describe atoms, 2 or more atoms that are bonded together covalently is a molecule. A molecule in layman's terms is really any small particle, but specifically in chemistry, a molecule is 2 or more atoms covalently bonded together. Okay, they're covalently bonded. In fact, sometimes the old word for this is molecular bonds. You'll sometimes see that even in your book. Molecular bonds. It specifically means covalent. So what's holding them together? Marriage? No, it's not the strong force. Not the weak force. You've only got 2 more left. Is it gravity? No. They're much too small to be affected in any meaningful way by gravity. So what is it? Electromagnetism. Yeah, just like the ionic bond, except instead of this case, instead of the positive cation attracting the negative anion, the positive nucleus of this one attracts all the electrons, and the positive nucleus of this one attracts all the electrons, but the electrons are still bound to their original atom. Now they're just drawn together because of that same electromagnetic attraction. So it's not that one oxygen attracts the other because one's positive and one's negative. It's that the nuclei of both oxygens attract the negative electrons of all of them. They share valence electrons together. They're held together by sharing their valence electrons together, right? Does that kind of make sense? By the way, this sharing of 4 electrons is called a double bond. 4 electrons, or we usually say 2 electron pairs. You see how those 2 things mean the same thing? So when they share 4 electrons, they're sharing 2 pairs of electrons. And we usually talk about it as pairs because they're always existing in pairs. The bonds are always existing in pairs. And so a double bond is 2 pairs. What do you think a single bond is?
1 pair.
1 pair. Let me give you an example. Give me another nonmetal. Give me a halogen.
Fluorine.
Fluorine. How many valence electrons does fluorine have? We're going to do the same thing. 1, 2, 3, 4, 5, 6, 7. How many valence electrons does fluorine have? 7. 1, 2, 3, 4, 5, 6, 7. Together, they can do the same or a similar thing. Oh, as another point of fact, recognize that the same number of valence electrons, right? How many valence electrons do we have up here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The same number. We didn't create more electrons. They're just sharing them now. In the same way, these ones all together had 14. They each had 7, so they have 14 altogether. How many should we find here? Also 14, and that is the case. So this one now, though, has 8, and this one has 8. How many are they sharing? Yeah, this is a single bond. 1 pair. 2 electrons or 1 pair of electrons. It's a single bond. What about, can you guess another kind of bond?
Triple bond.
A triple bond. Can you guess, based on this pattern, what kind of nonmetal might form a triple bond with itself? Nitrogen. Yep, great guess. How many valence electrons does nitrogen have?
5.
1, 2, 3, 4, 5. How many valence electrons does nitrogen have?
5.
1, 2, 3, 4, 5. Together, they're going to share how many, do you think?
3.
Well,
6.
yeah, they'll each share 3 for a total of 1, 2, 3, 4, 5, 6. How many does each nitrogen have now? How many valence electrons does each nitrogen have? 8, which is how it's most stable. They're satisfying still, in all of these cases, satisfying the octet rule. Satisfying the octet rule. And now this one has a triple bond, sharing 6 electrons, or 3 pairs of electrons. All of these 3 examples are what we call diatomic molecules. There are 7 diatomic molecules on the periodic table, and that is that these are more stable when they're bonded with one other atom of their own kind. So there ends up being 2, which is 2 atoms, 2 of the same atom, and there are 7. Can you guess what they are? I think we already talked about this. Yeah, so let's list them in order. There's hydrogen, first of all, because even though it doesn't satisfy the octet rule, hydrogen has 1 valence electron, 2 hydrogens together will share 2, and that satisfies hydrogen's octet rule. It fills its outermost level, which only has the room for 2. So hydrogen, nitrogen, oxygen, fluorine, and then down the halogens, chlorine, fluorine, bromine, and iodine. Each of them H2, N2, O2, F2, Cl2, F2, Br2, and I2. Of these 3...
Fluorine twice.
You're right, I do. Chlorine, fluorine, bromine, and iodine. Yep. Well, now I don't have fluorine twice. Thank you, though. Of these 3, which do you think is the strongest bond? And just using logic, what do you think is going to be the strongest bond here? Triple, yeah. 3 pieces of tape. This is a crummy way to think about it. But 3 pieces of tape hold your broken cell phone together better than 1 piece of tape. And that's a dumpy way to think about it. But another thing that I do want to point out from that is that shorter bonds are stronger bonds, always. And they take more energy to break. You'll know the answer to this, Fate. What does the N in TNT stand for? Nitro, yeah. Trinitrotoluene. The nitrogen-nitrogen triple bond is the strongest bond observed in nature, maybe ever. And the reason it's in things like TNT is because it takes an enormous amount of energy to break it, but when it breaks, it releases an enormous amount of energy. You know that all known biological organisms need nitrogen to survive, and there's a special kind of bacteria that can fix, that's the verb we use, that can fix nitrogen from the air. We're normally N2, which most of the atmosphere is. Remember, 78% of the atmosphere is N2, which we breathe in and breathe out, but it has no effect on us. We can't use that nitrogen. But there are certain bacteria that take a lot of energy and can break that nitrogen-nitrogen bond, and then that goes into the food we eat. And then we eat that food in the form of ammonia or urea or any other nitrogen-containing compound that isn't N2, and that's how we get our nitrogen. But the essence of all that is that shorter bonds means stronger bonds, and stronger bonds take more energy to break. The next thing we're going to talk about, we have a little time, don't we? Do we still have 10 minutes? Nitroglycerin, yeah, another nitrogen compound used as an explosive because it has so much energy. Do we have 10 minutes? I don't know what time it is. The thing at the 7 gets to the 10. So I've got 20 minutes. Okay, that's great because we still have a couple more things to talk about. Do you have questions about covalent bonding in general? One more thing about it is that there's this, you'll love this because of Gen Alpha. We have this idea of sigma and pi bonds, where a single bond, let's start with this one, a single bond is a sigma bond. It has to do with the way the electrons are arranged. Let me tell you it. I'll read it to you from the book. Single covalent bonds are called sigma bonds, represented by the Greek letter sigma. A sigma bond occurs when the pair of shared electrons is in an area centered between the two atoms. That's a sigma bond. And then there are also a double bond is a sigma, which is this letter, and a pi. And a pi bond is where the electrons are not actually between. So we indicate it in this way in our electron dot notation, but in reality, the electrons are not actually right between the atoms in the pi bond. And then a triple is a sigma and 2 pi's. So one
overlap and share electrons.
Yeah, a pi bond is where they are. Would you say they are overlapping? I think they're
parallel orbitals overlap and share.
Yeah, right. Parallel orbitals overlap and share electrons. So they're not between them. There's an overlap where they're sharing. So a sigma bond is a single bond. Oh, I should write a little letter next to it. A double bond is a sigma and a pi, and a triple bond is a sigma and 2 pi's. A little diagram that shows you here. I don't know. Is this showing up on the camera? Wait, this one?
Yes.
Okay. So you can see there's sigma bonds right in between those atoms, and then there's pi overlaps where there's the triple bond. Do you have questions about covalent bonds in general? We have 2 more things to talk about. That is, we're going to talk about how we name covalent compounds, which should be fast and easy. Usually people have an easier time with naming covalent compounds than ionic compounds. And then we're also going to talk about bond polarity. Do you have questions about covalent bonds in general, though? Any of you? Okay. Then I'm going to erase this and we're going to move on. So, as I said, the next thing we're going to talk about is how do we name these critters. I hope by now you understand the importance of naming these things, that in order to especially differentiate between different chemical species, it's important that we have different names, right? Even in the classroom or in your life, it's important that your friends and family have different names from each other or different things to call them so you know who you're talking about. In chemistry, it's the same way. In order to know which compounds we're talking about, we need to know how to correctly name them. And unlike your friends and family, you don't just have to memorize the names of things based on their character. There's a formula for it, which makes it a lot, frankly, easier, but it also makes it a little bit more difficult for chemistry students because you have to memorize stuff like polyatomic ions. So you'll remember ionic, sorry, what? Good? You remember ionic naming, but in covalent naming, we don't have a metal and a non-metal, so we start by naming the less, am I right? Either less or more. I've already written less, so hopefully that's what it is. Yeah, we name the less electronegative atom first. Electronegativity is how badly the thing wants more electrons. I'm going to write it professionally as the tendency to gain more electrons. So if we're defining it kind of colloquially as how bad something wants more electrons. What do you think is the most electronegative element? That is, which one wants electrons the most? Which one wants a new electron the most? First of all, where should I look to find atoms that want to or would be more stable gaining electrons? Where on the periodic table would I look to find atoms that would be more stable with more electrons? I'm looking right now for just an area. Which area of the periodic table am I going to look at to find ones that would like to gain? Yeah, the p block, the non-metals in the p block. Okay, so of those, which one would most like one more electron? The halogens is as a family. Yep, so it is a halogen. And so basically, would fluorine like one more electron worse, or would these bottom ones like one worse, or like one more? The answer is fluorine, because remember, its valence electron, all of the valence electrons it has are going to be held closer to the nucleus, and so the nucleus is going to have a stronger attraction to new valence electrons. So fluorine is the most electronegative element. Using that same logic, can you tell me what the least electronegative element is? So the most electronegative is fluorine. Nope. The least electronegative element altogether, the one that does not want another electron at all. Francium. Cesium might be, you might be right as far as naturally occurring, and maybe francium. Francium is technically naturally occurring, but it's in such small amounts. But yeah, francium wants to give up one electron so bad that we can think of it as it does not want to gain one more. And here's a table on page 265, which I'm also going to show the camera, that shows, is this showing up, the electronegativities of various, of all the atoms on the periodic table. This is, as far as I know, this is an arbitrary scale where 4 is the most electronegative something can be, and 0 is the least. And fluorine has an electronegativity of 3.98. So the less electronegative atom goes first. What we might even say is the more metallic. They're all nonmetals, but the more metallic one gets put first. And so, for instance, if we have phosphorus pentachloride, phosphorus has a lower electronegativity than chlorine, and so we put it first. There are no cations and anions in covalent bonds. They share, but phosphorus is more metallic than chlorine. Phosphorus wants electrons less than chlorine does, and so we put it first. So again, now we just name it. Phosphorus, the name, right? And then since there are 5 chlorines, we call it pentachloride. Do you remember these prefixes? What does penta mean? Can you guess? 5. And there's a different Greek prefix for each of the numbers. What's 1? You should remember these from physical science. Mono. What's 2? Di. What's 3? Tri. What's 4? No, that's Latin. Tetra. 5 is? 6 is? Hexa. 7? Hepta. 8? Octa or octo. 9? Nona. And 10? Deca. And the way that you recognize some of those is those are also the prefixes for the gons, like a decagon or an octagon or a hexagon. Those are all Greek prefixes too. And so you need to have those memorized. Actually, I don't even know if that's right. I think I give you a table of what the prefixes mean on the test. But we basically, if there is a number other than 1, we just put that in the name. And then sometimes, even in the case of like these two, this one is by far more common, so name this for me. Carbon dioxide. You've heard of that your whole life, and now I hope when you were a freshman you learned why it's named that, but now I hope you learn it again. And then this one we call, even though there isn't a number here, we do specify monoxide. We usually just use mono if there's a more common one that isn't one. So carbon dioxide is much more common, and in order to differentiate carbon dioxide, we call this one carbon monoxide. We might normally just call it carbon oxide, but we specify mono because there's a more common one that has 2 oxygens. So that's generally how we name and write the formulas. It's really usually a lot easier. This thing that I wrote, you're not really going to have to worry about this because they'll always be given to you in order. in both cases. The name and the formula, whichever one you're given, will just be in the right order already. But in case it comes up, if it says something like, a compound forms from 4 chlorine atoms and a compound forms from 4 chlorine atoms and 1 carbon atom, you have to know which one goes first, and in that case it would be carbon. Okay. Now let's talk a little bit about bond polarity. And that has to do with the electronegativity too. So I'm going to erase these, but I'm going to leave up the word for electronegativity. And we did talk about this also in physical science, but we kind of glazed over it a little bit. So polarity is how unequally the electrons are shared. So let me give you 2 examples. Okay, so here I have 2 molecules, right? This one is, what's this molecule? Yeah, O2. What's this molecule?
Hydrogen 2. Helium.
No. Oh, I think you're confused. This is not just a circle. This is the letter O.
Oxygen ion.
It's water.
Oh, you got. Oh, those are 2 H's.
Those are 2 H's. Yeah, I see now how that would be confusing. I'm going to do red for the oxygens. And we're going to start with you now see. I mean, is this a clear picture now that
yes.
you? Okay. We're going to start with this one so it's not confusing. Using either your logic or your electronegativity chart, which I just showed you and is found on page 265, or even just the picture itself, where do you think, if you were a valence electron, where do you want to spend most of your time? Around the oxygen or around the hydrogens? Around the oxygen. Oxygen has 8 protons, and you're more attracted to 8 protons than you are to 2 protons, right? And so the electrons mostly spend their time down here, giving it a partial negative charge. We use this Greek lowercase letter delta, which looks like that, or something like that. It's like an O with an S above it, kind of. The lowercase letter delta to mean partial charge. So because electrons spend more time down here, it gets a partial negative charge. What do you think that lends this end of it?
Partial positive.
Partial positive charge. And we use the partial because unlike in an ionic bond, where the calcium, from our example before, has a charge of +2 and the oxygen has a charge of -2, in this case, it's not quite a whole charge. It's not, as strong as the charge of a sodium ion or a chlorine ion or something. And so we call it partial positive and partial negative. But on this example, where do you want to spend more of your time? With the oxygen or with the oxygen? Neither. Yeah, they're the same. And so this bond is called non-polar. It doesn't have poles. The electrons don't want to hang out with either one more than the other. This bond is called polar. It does have poles. It has a negative pole and a positive pole. And the reason that's important is because if we have more than one water molecule, can you think of a situation where we might have more than one water molecule? Yeah, all the time. Almost every single time in the universe there's one water molecule, there's more than one water molecule. And they form intermolecular bonds. So not covalent bonds or ionic bonds, but bonds between the molecules. So if there's another, I'm just going to draw them a little bit simpler from now on, but if there's another group of, pretend these are all the same as that one, I'm just drawing them simpler so that I don't have to draw everything I just drew. So if there's a whole group of water molecules, the negative end of this one down here is attracted to the positive end of this one. A little bit weaker than an ionic bond, but that force of attraction between them is one of the things that gives water many of its properties. And that's called bond polarity. Do you have questions about that or about how to name them?
Nope.
Bye.